Hey guys, today we're going to talk about linear combination and spanning sets. So I'm going to go a little quickly here because my tablet's dying, so bear with me. A spanning set for R2. So what this means, a spanning set is any set of vectors, in which all other vectors in R2 can be created using, or can be created with. Okay, so the obvious example here is the one that we have talked about for the last several lessons, which would be I and J. Okay, using I and J, we can create any any vector within R2. Okay, so what's interesting is it actually turns out that it doesn't just have to be I or J. As long as you have two vectors in R2 that are non-zero and non-collinear, they will actually span all of R2. Okay, so any two vectors in R2 which are non-zero vectors and non-collinear will span R2. So in other words, any two vectors, it doesn't matter what they are, as long as they're not collinear, as long as one of them is not the zero vector, they will span, or we will be able to create any vector in R2 just by adding multiples of those vectors. Okay, so in other words, we've got, this isn't really an example, but the vector A here, we can use any two collinear vectors. So as long as, so if we can just say, so if we have U, which we'll just say is UX, UV, and V, okay, there exists M and N such that we would say A is equal to M times U plus N times V. Okay? So in M and N in this case would of course be scalars. We're just multiplying them by these constants. So regardless of the U and V, as long as they're not collinear, as long as they're not zero vectors, that will be true. Okay? So we're going to show that these two vectors, A and B, are spanning sets for R2. Okay? And so this is, what we're going to do is we're going to start, and we're going to go back to grade 10 and do a little bit of elimination. So the first thing I'm going to do is I'm going to create two equations. So my first equation, so I've got my vector x, or v, which is xy. So the x component here, the x component, if I have, we'll call it m and n, okay, if I multiply a by m and b by n, then x is going to be equal to m minus 3n, okay, and that's just because A's x value was 1, so 1 times m, and B's value was 3, so negative 3 times n. Okay. Similarly, I can create as my second equation y equals negative 3m plus 4n. Okay? So I've just multiplied vector A by m, I've multiplied vector B by n, and I've created these two equations. So now what we're going to do is I'm going to take equation 1 and I'm going to multiply it by 3. Okay, and what that's going to give me is 3x is equal to 3m minus 9n. Okay, so now if I do some addition here, if I add these two using my elimination, okay, I would have 3x plus y is equal to, these two are going to cancel each other out. I should do that in a different color. These two cancel each other out, and we're left with negative 5. Oh, for crying out loud. Negative 5n. Okay, because we have 4n minus 9n. All right, so this may not seem super significant, but what I can now do is two things. I can solve for n. Okay, so if I isolate n, I'll get negative 3 over 5x and minus 1 over 5y. Okay. And then I can take this equation and I can sub it into one of the other equations, and what I'll get is that m is, and I did this ahead of time, hopefully I didn't make any mistakes. I did do it pretty quickly, but I'm pretty sure I'm right. I got negative 4/5 x minus 3/5 y. Okay, and what this does, this may seem, you know, not terribly important, but this actually is enough to prove that in fact these two vectors span R2. Because regardless of what xy is, if I want to build any vector xy, I can figure out what the necessary n is, and I can figure out what the necessary m is simply by plugging in the x and y values that I'm given. Okay? So that actually does, so we can actually from that say therefore A and B span R2. All right, and that's that. Okay, so let's take a little look here at R3. Now, of course, there are spanning sets for R3, and we're not really going to get into that right now. What we are going to talk about is how if you have any two non-zero, non-collinear vectors within R3, they will span a plane in R3. Okay, a two-dimensional plane that exists within R3. Okay, so any two non-zero, non-collinear vectors in R3 will span a 2D plane. You don't have to actually say 2D. I'll put that in brackets. 2D. Planes are two-dimensional. When we say plane, it's always two-dimensional, but just so your notes are clear, just in case when you're looking back. Okay, a two-dimensional plane within R3, we'll say. Okay. So, if that's true, we have this thing called linear dependency. So if a vector if a vector lies on a plane spanned by, I can't spell, spanned by two vectors I guess it wouldn't have to be 2, it could be more, but regardless. So if a vector lies on a plane spanned by 2 vectors, okay, then this vector, vector can be created. Lots of definitions in this lesson. It's getting, it's a boring one, isn't it? Okay, can be created using those two vectors. Kind of a run-on sentence too. And is thus said to be linearly dependent. Okay. There you go. All right, so we're going to take a look here. So I'm giving you 2 vectors. You'll notice these exist in R3. They're 3-dimensional vectors. Okay, we want to know, can I create the vector C by using these other 2 vectors? Or in other words, does it lie on the plane that is determined by A and B? This is this plane that is spanned by A and B. Okay, so what I'm going to do is I'm going to start out by writing out, and I'm going to use a version of writing vectors that I haven't used very often, hardly at all. But this is one. This is actually the version that a lot of people, as you get into more advanced math, often prefer. Is if you write a vector just like that. So that's a vector. This is your x. That's your y, and that's your z. Okay, it's no different, but anyway, so you don't, the stuff I wrote in blue, that's just a note, that's not part of the equation, but anyway, so we'll take m, we'll have a constant m, and we'll multiply it by -1, 2, and -3, so this is our vector A, okay, I'll write that in blue as well, so that's vector A right there. Okay, you'll notice because you use these square vectors and line them up on top of each other, you don't actually have to use the arrow that we do when we use normal coordinate notation. Of course, your textbook doesn't use the arrow on top anyway, which is a pet peeve of mine that they don't do that. But anyway, there we go. And you'll notice that this is, of course, vector B there. Okay, so there exists some m and some n such that when I multiply them by A and B, I can create this vector C here. Okay, so we're going to find out what m and n are, or if they do in fact exist. Okay, because if of course this vector doesn't lie on the plane, then there will be no m and n that actually satisfies this. So we're going to start by creating 3 equations this time. Okay. 3 equations. So the first one is just -7 equals -m. I just did -1 times m plus 2n. Okay, my second vector will be 6 equals 2 times m, and it would of course be plus 0, but I don't need to write that. And then our third one is -7 equals -3m minus n. Okay, so there's our 3 formulas, and it's not hard to see which one we're going to start with. We are going to start with equation number 2, because using it, we only have to divide by 2, and we see that m is equal to 3. So there's our first variable solved for. Okay, now keep in mind this might not actually work, in which case we might try to sub this in and it's just not true, and we'll see that m does not in fact equal 3. But that's the hope, is that it equals 3. So now we'll take equation 1, okay, and we have -7 equals, and I'm going to sub in this 3 for m, so I've got -3 plus 2n, which of course tells us that, oh well, I better not skip steps here, so we got -4 equals 2n, okay, or n equals -2. So there's our second one. So we've used equation 1, we've used equation 2. So what we need to do now is we need to look at equation 3. Okay, but what we need to do is we need to see, is equation 3 actually satisfied? So we'll just start by saying -3 times 3 minus the -2. Okay, I guess I should write, hold on, I'm going to write, put that out of the way. I'm going to write it out because just so that you see, so that it was -3m minus n is what it was. Okay, so I've subbed in the m, I've subbed in the n. Okay, so I get -9 plus 2, okay, which is -7, and that is exactly what we were hoping for. Okay, so therefore, yes, okay, it does indeed span, it does lie on the plane spanned by A and B. Okay, so I want you to try part B on your own. It's not very different. In fact, it should actually be fairly quick to figure out. But I want you to take it up with your partners in class tomorrow. So until next time, go Sabres!